In this video, I'm going to talk about a new topic called Routh Hurwitz Criterion or Routh Hurwitz method or Routh stability criteria. Everything is same. Routh and Hurwitz, they are two different scientists who proposed this method. So basically, by using this method, we can find out stability of a system. Actually, we can find whether that system is stable or not. So what is stability? So here is an example. We'll talk about stability in a minute. Here is an example. H of s equal to s plus 1 over s minus 1, s minus 2, s minus 3. Okay. So I think I told you many times this is called characteristic polynomial. Okay. A denominator of a transfer function, we call that as the characteristic polynomial. When we make it equal to 0, we call that as characteristic polynomial equation. So here, this characteristic polynomial equation represents the poles of a system. Okay, so this this characteristic polynomial equation, it's a third order characteristic polynomial equation. So it has three poles. Those three poles are s equal to 1, s equal to 2, s equal to 3. Okay, all these three poles. So if you look into the xy plane, s equal to 1 is right there, 2 right there, 3. All these poles are on the right hand side of the y-axis. Okay, if it is right hand side of the y-axis, then that system is not going to be stable. It's not a stable system. So basically, if you build a circuit, okay, and that circuit has a pole and that circuit has a transfer function like this, and at least one of the pole need not to be all the poles, even one pole. So in another case, say for example, s equal to let me write down another case, s equal to minus 2, s equal to minus 3, s equal to 1. So this is another case. That's minus 2, that's minus 3, another pole, and 2 and 1. Here is another pole. So both of these cases, okay, the system is unstable. Okay, so as I mentioned, so this is an unstable system. This is also unstable system. So as I mentioned, if system needs to be stable, system will be stable if and only if all the poles are on this side of the y-axis. Okay, need not to be on the x-axis. It could be anywhere on this y-axis. So this is x-axis, y-axis, anywhere in this region. That's what. So that's how a system, we can define a system is stable or not. Now this Routh Hurwitz criteria, here I have only three poles. Okay, but most of the times, I mean, you can clearly see those are you can clearly see the poles, but most of the time you have an equation something like this: s to the power of 10 plus 9 times s to the power of 9 plus 7 times s to the power of 8, blah blah blah. So this system has 10 poles. Okay, so finding 10 poles from this characteristic polynomial equation, there is lots of math involved. Okay, now what we can do by using Routh Hurwitz criteria, without finding the poles, we can find out the stability of the system, whether that system is stable or not. That's what we can tell. We cannot tell what are the poles, how much stable, what needs to be done to stabilize it. We cannot tell by using Routh Hurwitz criteria. Let me start with a simple example, then you will understand a little bit better. So here is an example. Here is a characteristic polynomial equation. From this characteristic polynomial equation, we are trying to find whether this system, so the system is stable or not. Where did I get this characteristic polynomial? This characteristic polynomial, I got it from the transfer function. H of s equal to u of s over y of s. Okay. This y of s, so basically whatever you have in the numerator, the denominator, this is right there. Okay, but at the same time y of s is not equal to this though. Okay, this whole thing represents the transfer function. Now what we're going to do here, we're going to do arrange these coefficients of S in a different way. That way is called Routh's array. We call it as Routh's array. Okay, we're going to arrange them in a different way. So first I'm going to put S to the power of 4. Now here, write down all the coefficients of even s's. So S to the power of 4, S square, and constant. Now I'm going to put S cube. Here I'm going to put all the odd number constants. So 10, 5, if needed you can put 0 or leave it as it is. Now I'm going to tell you how to find. So we have to solve it until we reach S to the power of 0. Okay, I'm going to label these letters as A, B. Sorry, I'm going to label them as A1, A2, A3, something like this. B1, B2, B3, C1, C2, C3. Okay. Now I'm going to tell you how to find A1. To find A1 equal. To find A1, okay, we're finding this element. So take this matrix right there, 3, 5, 10, 5. Okay, to find A1, multiply these two. Okay, 10 times 5 minus, multiply these two, minus of 3 times 5 divided by, put this number right here in the denominator, 10. So this will be 50 minus 15 over 10, which is 3.5. Okay, or you can say 7 by 2. That is my A1. Now I'm going to tell you how to find A2. Okay, to find A2, let me erase this. Oops. Okay, to find A2, I'm going to use these two as well as these two here. Since I don't have any element here, I can take that as 0. So to find A2, I'm going to put them on the side, but with practice you don't need to do that. Okay, so it's going to be 10 times 2 minus 3 times 0 over 10. Okay, so 10 times 2 minus 0, which is 10 times 2 divided by 10, which is, it will give you 2. So I found A1 and A2. Here A3, since I don't have any more element, A3 is going to be 0, so I don't need to worry about A3. Okay, so I'm not putting A3 there. I'm going to replace A1 and A2 here. So this is 7 by 2, this is 2. Okay, next part is I'm trying to find B1. So to find B1, okay, take the above two rows, make that as a matrix format. So I have 10, 7 by 2, 5 and 2. Okay, so multiply these two, 7 by 2 times 5 minus, multiply these two elements, 10 times 2 divided by 7 by 2. So we'll end up with, okay, after simplifying this, I end up with B1 equal to minus 5 by 7, not 5 by 2, it is 5 by 7. Now same way we're going to do B2, but to find B2 here, okay, to find B2 we're going to use these two elements and then these two elements. Since I do not have any element, I can put 0. Anyway, 0, 0, so it's not going to be worth it. It's going to be 0, so you don't need to find B2 or B3. So I found B1, that B1 value is, I have minus 5 by 7. The remaining elements you can put 0, 0, 0. Doesn't matter. Okay. Now I'm sure C2 is not going to exist. It's going to be only C1. So find C1 in this. So to find C1, what I'm going to do, let me use, I'm going to use blue here. So C1 equal to find C1, take about 2 rows, okay, which are these two. Now make these 4 elements as a matrix and find C1 equal to, multiply these two minus, multiply these two divided by this, so we'll end up with C1 equal to 2. Okay, C1 equal to minus 5 by 7 times 2 minus 7 by 2 times 0 over minus 5 by 7. So we'll end up with, this is 0, minus 5 by 7 minus 5 by 7 get cancelled out, we'll end up with 2. So I have C1 equal to 0. I'm sure the remaining elements are going to be 0 if you find this. So to find the remaining elements, you have to keep the first column as it is. Every element you're changing the other columns. Okay. Now the important part is right here. We'll look into the first column. Okay, when we look into the first column, see how many times the sign is changed. So the first one plus 3, second one plus 10, so there is no sign change. Plus 10 to plus 7.2, 7 over 2, which is, there is no sign change. 7 over 2 to minus 5 by 7, so there is a sign change. So the number is changed from positive to negative. And again minus 5 by 7 to 2, again sign is changed. So the sign changed twice. So this system has 2 unstable poles. So the important point is number of sign changes equal to number of. So here the important points you need to know: the number of sign changes equal to number of unstable poles. The number of sign changes in the first column. Okay, so at the same time, if there are no sign changes, then all the poles are on the left side of y-axis. That is, all poles are stable poles. So if you take the xy axis, so if all poles are on this side, y-axis side, then that's those poles are stable poles, so system is stable there. So in this example, we saw there are 2 sign changes. In this example, we saw 2 sign changes. So we have 2 unstable poles. Okay, so this system is unstable. So basically, Routh Hurwitz criteria or Routh Hurwitz method tells us that whether the system is stable or not. It doesn't give you what are the stable poles, what are the unstable poles. It tells you only how many number of unstable poles are there, whether the system is stable or not. Okay, that's all. Thank you. I will make more videos based on these examples. Okay, thank you.